Hello everyone, welcome back in the course of higher surveying, and today we are in the new module on LIDAR. In this module we are going to talk about the LIDAR grammetry or LIDAR. This module has 4 lectures. The first lecture is about the fundamentals of the LIDAR. For this module, this is the book we recommend, Topographic Laser Ranging and Scanning Principles and Processing by J. Shan and C. K. Toth. Again, I urge you to join some library to avail this book. So, let me give you historical perspective why LIDAR has emerged as a new and alternative technology to the existing technologies like photogrammetry or radar. In 1990s, when analytical photogrammetry was on its peak, still it was facing some limitations. The first limitation was related to high photographic resolution. That means the photographs were acquired at very high resolution, 150 lines per millimeter or 250 lines per millimeter. However, when these photographs were converted to the soft copy images by scanning, that scanner resolution was the real limitation. When I was a student, maximum resolution which was easily available was 2400 dpi. In 1990, 2400 dpi was very high resolution in those days. That was the first limiting factor. Further, for photogrammetry, we have to have the stereo photographs. For the stereo coverage, a lot of planning was required and it was a cumbersome process. And secondly, the logistics of the aerial photography was always there in place. After processing the 2D images, we used to get the 3D data. The accuracy of the aerial triangulation or the bundle adjustment was around 2.5 pixel best, and pixel size was very large, some few meters. What about the digital photogrammetry? The digital photogrammetry was in the place, but it was in the evolving stage, and the algorithms like SIFT or SURF were not in place. And the cameras which were using the films, they were very expensive as well as large in the size. Moreover, digital cameras were in the evolution stage, they were also very expensive and large in size also. So, these were the all limitations that give rise to an opportunity that we should have some technology that can give a direct 3D data without GCPs, and it was a natural opportunity to emerge a new technology. LIDAR is one of such technologies that emerged due to some limitations of other technology. So, let us go ahead and try to see how LIDAR works. LIDAR is an abbreviation for light detection and ranging. LIDAR uses the laser light. So, what is the laser and how is it useful in order to do the ranging and detection? Laser is an acronym for light amplification by stimulated emission of radiation. So, it has certain characteristics like wavelength, coherence, duration of emission, beam divergence, output power and power requirements. So, we are going to learn the laser in a comprehensive manner. Before that, first understand what do you mean by stimulated emission and spontaneous emission. What is spontaneous emission? We know by the quantum physics that if there is a nucleus of an atom and there are orbits of electrons like this, so they are a fixed level of energy. This could be, let us say, electrons which are moving in these orbits. These electrons get some energy and they go to this level. Later on, they release the energy and again come back to their original state, and during this process they release energy. So, energy is released as a photon. This process is called the spontaneous emission. Surprisingly, this photon is having some wavelength. A photon, which is energy particle, how can it have a wavelength? Light has dual nature. When light travels in the space, it behaves like a wave, but when it interacts with the surface, it behaves like a particle. So, that is why we can say that the photon, when it travels, it has some wavelength. So, the spontaneous emission is releasing some energy at certain wavelength. These photons have different wavelengths, and that is why we see the white light. It has the photons of all wavelengths. So when all wavelengths lights are mixed, they create the white light. Another example is electrical bulb. In case of electrical bulb, electricity is supplied to the filament. Photons which are emitted by that filament material, that is another example of the spontaneous emission. So what is the effect of the spontaneous emission? Whatever color we see of any material, it is because of the spontaneous emission. Let us go ahead to the stimulated emission now. In case of stimulated emission, we deliberately stimulate atoms by giving energy, and that energy is released in form of photon, then it will have certain wavelength. Now imagine that all the photons which are released by atoms are in the same wavelength, and because of that they will give the same color, and we characterize the color by the wavelength, so they are giving the same color. Now what do you mean by stimulation? So we are stimulating the atoms so that they are excited, and in the excited state one photon is released by one atom, and that photon will trigger another atom. So now we have two photons. These two photons will trigger two more atoms. Then we have four photons, and that is why it is called the process of amplification in stimulated emission. So now first of all we have simulation, then we have the amplification. Because of that we have a stream of photons available after certain duration, and that creates the laser. Now you can understand what do you mean by stimulated emission and what is the must condition. The must condition is, first of all, I should have the photons of the same wavelength. One more condition is required here, that these photons should be of the same phase. That means the wavelength are not only same, but the waves are also having same phase. And we will talk about these two characteristics in coming slides. So we generate the laser by the stimulated emission. Let's go to the wavelength. As I told that all the photons which are triggered by the stimulated emission, they have the same wavelength. As a result, they are monochromatic. That means they produce the light of one color or light of one wavelength. The reason is that it is not all the photons have the same wavelength, but their wavelengths are in a very small range. The laser is available in the infrared, visible and ultraviolet ranges. What about other ranges? For example, gamma ray, X-ray or microwave. We do have the lasers in these ranges also. Gamma rays and X-rays lasers are very harmful for the human, and that is why we do not prefer those. At the same time, microwave, which is having very higher wavelength, even laser can be generated in that range. However, that will not be so accurate for the topographic mapping, and that is why we also avoid the microwave lasers. We have the laser that emits lights of two or more colors. It's called multi-line lasers. That means it is having certain wavelengths. At those wavelengths it is emitting the light. Now coming to the next property, coherence. All the photons in laser are having the same phase. Before explaining you the coherence, I would like to give one simple example. During the march past, the soldiers are moving their hand in one rhythm. That means when all the soldiers are moving, so they will either raise their hand or they will lower down their hands. So if all the soldiers are moving in a rhythm or in the same phase, and they are moving along a certain direction on a straight track or maybe a curvilinear track. If you assume that each soldier is like a photon and their movement is like a wave and their hand movements is like having the same phase. So that means a wave is moving with photons. Now you got the concept, what is the wave and how photons are moving in same phase. So what does it mean? I am drawing the wavelength of a wave like this. Let us draw another one. If they have same wavelength and same phase, so wavelength, this is same wavelength I have here. They have the same phase also because peaks are matching or the valleys are matching here. And because of this, in case of coherence, the phase is same. And that is what the laser has. All the photons are having same phase. What is the advantage here? The advantage is, first, they are monochromatic, and so they have the same color, they have the same wavelength. Not only that, once they are in the same phase, and so that shows coherence for a very long distance. And I can give you a simple example here. We have two wavelengths. Let us say there is some wavelength difference. So, this is the first wave, and the second wave is slightly different. So, it is like this. So, this is the difference of the wavelength here, delta lambda. This is total lambda. So, this is delta lambda. You can see here that as two waves are propagating, at every one cycle they will accumulate the difference of delta lambda. So, after n number of cycles they will accumulate some amount of lambda, the some amount of difference of phase, and let us say that phase has changed after n cycles. So, it becomes lambda by 2. Now, let us take that delta lambda is 0.001% of lambda, which means lambda into 0.001 divided by 100, or I can say 10 to the power minus 5 lambda. If I put this value here, what will I get? N into 10 to the power minus 5 lambda equal to lambda by 2, lambda got cancelled, and n is equal to 10 to the power 5 divided by 2, which is 5 into 10 to the power 4 cycles. So, after these many cycles, these two waves start showing the destructive interference, because their phase are completely changed, that we do not want. If lambda, let us say this value 1000 nanometer, n into lambda is 1000 into so many meters into n, what we call here 10 to the power 4, and that gives 0.05 meter. That means within 5 centimeter these two waves of laser will become completely uncoherent, and that is why we can say what is the tolerance of delta lambda. That means how delta lambda is very small, extremely small, such that the coherence is achieved in case of laser. If this 5 centimeter is 500 meter or 5 kilometer, you can find out what should be the delta lambda value. Try it yourself, try to find out. So, I hope that I have explained you what is the coherence and what is the meaning of the monochromatic. Same wavelength is monochromatic, and what is the meaning of coherence? Waves having the same phase. Let us go ahead. One more property comes here, the duration of emission. Let us assume that you have a laser torch. This is a laser torch. Turn it on and keep it turning on. As a result, the laser photons are being emitted by the laser torch. So, they are emitted and they are traveling. The continuous stream of laser photons will create a wave. So, these continuous stream of the photons, they will go, they will interact with the surface, come back, and then we measure it again. And we try to measure some kind of attribute in the space, maybe the distance or maybe some other characteristics. Now, there is another concept called pulse. Let us say you have a torch and you click it, turn it on and turn off. So, during that short duration of turn on to turn off, the torch will emit certain number of photons for a very short duration, and that is what we call the pulse. Those number of photons will travel now, they will also interact with the surface and come back, and again we will measure those, and so we are measuring the pulses now. So, best example of pulse is our heartbeats. Our heart vibrates like this. So, it gives 72 pulses in a minute. Sometimes you might have seen some medical experts, they measure the pulses on the wrist of a patient. What does it mean? Basically, they are trying to count that how many pulses or signals are coming into that small duration of 1 minute. If it is around 72, well, patient is okay, its heart is working well. However, if it is otherwise, they take the cognizance of that. The idea here is the heart is also creating some pulses, or heart is vibrating. So, it is kind of creating a pulse. That means it is making on, off, on, off. So, we can see here that there are some short pulses and long pulses. So, what is a short pulse? A pulse which is triggered in a short duration is called short pulse, and comparatively if the same number of photons are triggered in a slightly longer duration, it is called long pulse. But there is a condition in general when we call there is a pulse, which means it should be triggered within a second, and that is why we have more number of pulses triggered in 1 second, at least more than one pulse we have. What about the focused pulses? Once pulse is triggered, it travels in the space, it interacts with some surface area of the object, and if it interacts with the larger area of an object, the number of photons will be divided over that surface, and the returned signal will be weaker because the number of photons are fixed and they are interacting with large area. However, if the pulse is focused, it will interact with very small area, and number of photons that will be responded back will give better information or pinpointed information. So, focused pulses can illuminate a small spot with high energy. I hope these concepts are now becoming clear to you. Also, the short pulse is the short duration over which we trigger some photons, hence they are more intense because over the short duration we are triggering the same number of photons, they are traveling, they are interacting with the surface, and they are reflected back. So, they will be definitely more intense because they are interacting in a short duration compared to a longer duration. In case of pulse, we trigger the photons in a very short duration. Those photons travels in the space, interacts with the surface, come back, and so we measure the time difference between the triggered pulse and the received pulse, and we try to measure the distance based on the time of flight or time difference between the triggered and the received pulse, and this is called the time of flight principle. On the other hand, in case of wave, we are continuously triggering the photons over the time. Wave goes, interacts with the surface, comes back, and we try to measure the phase of the two waves. One is triggered and another is received. So, the difference of phase gives the information about the distance from the laser emitter or receiver and the object. The wave-based principle we have already seen in the basic surveying course, where we have learned all the modulation techniques and so on. So, these are the same thing, but the time of flight principle is different. For topographic mapping, time of flight principle is more popular for longer distances, which are in kilometers, and that is specific to the LiDAR. For a pulse, what are the attributes that helps to do the topographic mapping? So, let us see power and time curve. This is pulse. So, that is the longitudinal profile of a pulse. It looks like a normal distribution curve, and we can model it also like that. This is peak power PT. So, this is 10% of the peak power, and these are the 2 points, this point and this point. If I take this level here and try to find out the area of the power time curve, you will be surprised that the area under this curve, if I assume it to be normal, it is approximately 98.99% of the total area, or which is I can say 99%. Apart from that, if I see 90% of the peak power, so I have marked these 2 points. So, from this point here to this point here, longitudinal profile is rising up, and so we call it the rise time of a laser pulse. Similarly, from this point here to this point, longitudinal profile will fall, so we call it the fall time. We are triggering the number of photons in short duration. So, it reaches to the peak power, comes back very fast. So, rise time and fall time are very small. Now, I want to model this laser pulse or the longitudinal profile of the laser pulse. We define a third level, which is 50%, the half of the maximum. Then we draw this rectangular box. If I calculate the area of this rectangular box, then it is equal to the almost 94% of the total area under this curve or under the longitudinal profile of a pulse, and that is why this rectangular box is a good approximation, and the corresponding time length, which is shown by the arrow here on the screen, it is called full width at half maximum. I repeat, full width, which is this width, at half maximum, because we are considering only 50%, which is half of the maximum. FWHM is known as pulse length. So that is pulse length here, full width at half maximum. And now we can say energy of a pulse is equal to peak power into FWHM. That means energy contained within a pulse is equal to peak power into the pulse length. So now I have approximated the laser pulse, which is normally distributed by a rectangular box. It is easy to make any estimate with the rectangular pulse. So as I told already that short pulses are there. So we are triggering more than one pulse in a second. And suppose we trigger n number of pulses in 1 second, how much energy do I need to trigger n number of pulses? And each pulse is having this much of energy. So that is average power I need in order to trigger n number of pulses, each having E energy. So now you can see we are triggering pulse over a very short duration, which is FWHM. PT is very, very high, sometimes 2 kilowatts, because the 2 kilowatts is concentrated over very short duration. And that is why we can have n very high. That means I can release sometimes 10 to the power 5 pulses in 1 second. And that is an advantage of the laser. And that is why we want to use the laser, so that we can acquire the data at very fast rate with high accuracy. Now try to understand the beam divergence. As I told that the laser is a light. It behaves like a wave also. So it diffracts, it refracts, it reflects, it gets polarized, and so on. So now there is a laser light source and it has some opening, and because of that opening the laser light is diffracting at the corners of that opening, and as a result it will create a spot, or it will illuminate some area on the object surface. So this is distance d. This spot is created by the laser pulse. Area of interest is the center red point. However, a spot is created by laser pulse. So the laser spot is ambiguity, because I am thinking that the laser pulse is reflected back from this point. However, this is reflected from this whole area, and I do not know which part is more reflective within this footprint. Let us say that this part is reflecting more energy compared to the remaining part of the footprint or the spot. I assume that this red part is located at the center. So laser spot is a ambiguity or the uncertainty in the position of point. So this is beta angle, which is called half beam divergence. And now increase the distance d. Because of the increase in the distance d, the laser spot size will increase. And now you can understand that as we increase the distance from the light source to the object, ambiguity will increase. Now the radius of the laser spot is given by d tangent beta. Moreover, if beta is very small, I can make it equal to d beta. So the beta is half divergence angle, and the divergence angle or the beam divergence is theta, which is equal to 2 beta, is given by 2.44 lambda divided d. D is size of the aperture of the transmitter or size of the opening of transmitter, and lambda is the wavelength of the laser. You can understand that if I want to reduce the ambiguity or uncertainty in the position of this point or maybe this point, I can reduce the lambda. Again, few slides back I told that reducing lambda has some limitation, because it is not good for the biological life or human life. And that is the reason we always have some limitation on the laser pulse or laser wave. So now try to understand the property output. As I told that we give some energy to atoms, and atoms are stimulated, and as a result they give the laser. The output power is the strength of a laser beam. That means the number of photons which are released in short duration or as a continuous wave, they are released in certain time. So the amount of energy released by the photons in that time duration, it is creating the concept of power, which is a usual concept. What is the output power? energy release divided by time duration of energy release. So, that is the power of the laser pulse or laser wave. What is the output power range? For laser, it is in the range of milliwatt to kilowatt, but a particular laser has only certain level of power. It can be milliwatt, it can be kilowatt, or it can be intermediate value, but it will be certain value. Now compare the pulse and the wave. Wave is a continuous emission of the photons, so it has low power. On the other hand, in case of pulse, we trigger the number of photons in very short duration, and as a result we get the peak power, and the peak power is very high in case of pulse. So remember these things. They are very simple things, but they are very useful in terms of distance measurement concepts, because if a pulse which is having very high power over a short duration, it can travel to a long distance. At the same time, the continuous wave, although it is having the continuous stream of the photons, but average energy is very less, so it will travel for a shorter distances compared to the pulse. And that is why for topographic mapping, where the distances are very high, 1 kilometer, 2 kilometer, we prefer the pulse, or we prefer the time of flight principle, or we do measurement by time of flight principle. What is the power requirement? So laser is using electricity. Efficiency is somewhere very low. The minimum efficiency is 0.001%. That means if I give 100 watts, you multiply by 0.001%, that will be the output of the laser pulse of wave. At the same time, the maximum energy is 30%. The remaining energy goes into the heat generation. So that is somehow a limitation also. That means we have to do continuous cooling. So now we have learned what is the laser and what are its characteristics. I want to do the range measurement or the distance measurement using the laser pulse or maybe the laser wave. First start with the laser pulse. So let us understand how do we measure the distance between the transmitter or receiver of a laser and the object surface. This distance could be inclined, this distance could be vertical. It is very important to understand that by triggering the laser pulse or a wave, we are sending some energy. The energy photons are interacting with some surface, reflecting back, and they are coming to the receiver. So we are again measuring energy there. So we should be able to measure the energy again. Once we trigger, we will note down the time or we will note down the phase, and laser pulse or wave comes back to receiver. We will measure the time again or the phase again, whatever. And then we measure the difference of time or phase in order to determine the distance between the receiver transmitter assembly and the object surface. So let us see how do we measure the energy. So that is transmitter here, and it has some aperture. There is a range R. So this is the illuminated area, and this is a laser spot which is shown here by illuminated area, and we also call it footprint. So this is the cone of the transmitted laser pulse. So now this divergence angle 2 beta. So we have 2r tangent beta as footprint or laser spot diameter. We call it footprint in case of topographic mapping. I can approximate it by 2r beta. We can see here the transmitted power of a laser is Pt. It is passing through the atmosphere and it is getting attenuated. That means its power is reduced by the atmosphere. And so we define a coefficient m, which is absorption coefficient of atmosphere. So we have the transmitted power as Pt, and then we have power received at ground or object through the atmosphere is this much, and m is less than 1. That is why we receive power of the laser at ground surface less than Pt. You can see this is the illuminated area Ai dt with opening of transmitter, and then d is distance or the range r here. So here d is equal to r. So we have 2r tangent beta. Now what is the irradiance? So far this is the area in meter square, and here it is the power in watts, and here it is power in watts. If I divide this power over this illuminated area. So, I can find out what is the power available at unit area. So, we call it the irradiance, and irradiance is measured in watt per meter square. Now, you can see that how much power is received on the unit area of the illumination. So, within the illuminated area, let us assume there is a target and it has an area AT. The power received or the power of the pulse at the target, it will be this much. So, again it will be in watts. This target within the illuminated area is reflecting the pulse. So, the reflectance is rho, which is again less than 1. It will allow this much power to be reflected back like this. So, target is reflecting power in all the directions. If I assume a hemisphere around the target, we can say that in unit solid angle of the hemisphere, how much energy or how much power is being reflected by the target. So, this is the power reflected per unit solid angle of target, because we are dividing it by pi, which is the solid angle of hemisphere. The power of the reflected pulse received at the receiver, because again it is travelling through atmosphere. So, again we are multiplying with the m. So, it becomes m square. This is the power that is received at the receiver. Receiver also is having an opening, and in that opening only the energy or the power will be detected. Now, if I consider the hemisphere around the receiver, this is the solid angle framed at the receiver, and in this angle only reflected power is reaching to the receiver. So, the power received at the receiver in solid angle of receiver. This is the solid angle of the receiver, and so what is the irradiance at the receiver, which is phi r. So, I divide this power by AR. So, I will get this term, and this is what we call the LIDAR equation. So, we have just seen that how to derive the LIDAR equation, and that says that if I have a laser pulse of PT peak power, I will have this much irradiance in watt per meter square at the receiver, and if I can measure this much amount of laser power, I can do the range measurement from the transmitter receiver assembly of laser instrument to the target. What about the energy at receiver? Let us say there is a pulse which is reflected having PR as a peak power, and if we say that the Tp is the pulse length of the received pulse, so that is total energy of the received pulse. Okay, what about the number of photons of the received pulse? Er divided by h nu, where h is Planck's constant and mu is frequency of laser pulse. Let us say we have a laser transmitter, it has fired some number of pulses together. So, they are all coming back. So, we are not able to distinguish, because the laser pulses are travelling with the speed of light. Because of this high speed, what is the consequence? We cannot fire all the pulses in a single moment. So, what do? We fire these pulses sequentially, one by one. So, one pulse is fired by a transmitter receiver assembly here, interacting with surface, comes back, and then we fire the next pulse, it interacts, comes back. This process is called sequential firing. Because of this sequential firing, we have certain limitation. The first limitation is that if I increase this distance, which is d or range r, a pulse will take more time to return back. and as a result I can fire some limited number or less number of pulses if distance is high or the range is high between the transmitter receiver assembly and the surface. R is high, that means a pulse has to travel along, it needs more energy, that means I have to increase the peak power of the pulse. And if I increase the peak power of the pulse for a given constant power in input, we have the average power E here or average energy, which is Pt into FWHM into N, that is average energy. So, the moment I increase the Pt, number of pulses fired per second will be less, because I am firing less number of pulses, and automatically I will have less details. So, that is concept we should understand. If distance is higher, pulse will take more time, and as a result I can fire less number of pulses during 1 second or during operation of the range measurement. At the same time, in order to travel long distances, we need to give more energy to each pulse, and as a result the number of pulses will reduce for a given average energy which is available in the form of battery power. I hope that you understand this concept of sequential firing. So, we have learned how to measure the reflected signal after triggering a pulse or maybe wave. Now, let us see the time of flight principle. How do we do it exactly? That means how to measure the time difference of the triggered and reflected pulse. So, let us see there is a power and time curve. So, this is peak power of modeled laser pulse, which is rectangular in shape. If the reflected pulse is having some threshold, I will assume that the signal has been received or the reflected pulse has been received and it is a valid signal. So, if this is the reflected pulse, I will assume that it is not being received. At the same time, if this is the laser pulse, that this is returned pulse and it is crossing certain threshold. So, I will mark this as point here. So, this is T2, the time, and this is T1 time. So, this is time of triggering the pulse and this is the time of return pulse. If I measure the time difference T2 minus T1, it will be delta T, and now I can find out the range as C, which is velocity of the light into delta T divided by 2. This time difference T2 minus T1 is equivalent to the 2 times of the range, because pulse is going and it is coming back, and that is why we divide by 2, and that is range between the transmitter receiver assembly and the object surface. So, what about the accuracy of this measurement, or what about the resolution of this measurement? Resolution of this range is given by C times divided by 2 into the accuracy of delta T. So, that accuracy of the time measurement or time of flight measurement will decide resolution, that is the minimum distance we can measure by a laser pulse. I hope you got the idea. Now, multiple returns. What happens in case of LIDAR? This is the illuminated area or footprint. Let us say there are 3 objects, object 1, object 2 and object 3, which are located in one footprint. Energy which is passing through the atmosphere, first it will interact with this object 1 here, then the energy which is not interacting with object 1 will pass through and it will interact with object 2, and later the remaining energy or the remaining power will interact with object 3, and as a consequence of that we will get multiple return pulses, first from object 1, then from object 2 and then from object 3. This is peak power Pt and this laser pulse which is triggered one. So, this is timestamp T1, this is threshold value, and now for object 1 this is the return pulse, for object 2 this one, object 3 this one, and all these 3 objects are considered to be in one footprint. That means they are along the one line, although in the last slide we have shown them slightly here and there within one footprint. However, the laser pulse will report that all 3 are in one line along the center point of the laser pulse. But no doubt it is giving us one advantage: we are getting multiple returns, because there is a space available between the object 1 and object 2 and object 3, and through that space the laser pulse is traveling, it is passing through atmosphere, and so it is giving the multiple returns. You will be surprised, this is the only reason we get the tree structure, because the tree canopy has some voids, and through those voids the laser pulses pass. That means they partly interact at certain level of leaves, and then the partly pulse will pass through the void, and again it will interact with the another layer, again it will pass through that only, and so we get multiple returns. And by using the multiple returns we can completely understand, or we can completely map a 3D structure of a tree, and that is the beauty with the LiDAR. I hope now you can appreciate why do we have the LiDAR in place today. It is being extensively used by the researchers and industry also. These are the different pulses. So this is timestamp T2, T3 and T4. So if I take the time difference of T1 and T2, I will find out what is first return distance or range. Secondly, for the second object, I can find out what is the range of second object from the transmitter, and similarly I can find out for the object 3. And now if I map those objects along that particular line, I can find out what is the height of particular leaf, second leaf and the third leaf, or maybe the ground surface. So today it is possible to receive 4 returns. So let us see what is the range and accuracy. As I already told, the range is c times delta t, and so we have the accuracy of delta t, that is the time measurement, and that decides range accuracy or the resolution of the laser pulse. Similarly, in case of phase based principle, we measure the phase difference delta phi, and the distance r is given by 1 by 2 m number of cycles, so m lambda plus delta phi by 2 pi into lambda, that we have already seen in case of total station, and the same expression I am writing here. So what about the accuracy or the resolution of R? As we have seen in case of basic surveying, we can achieve an resolution of R as lambda by 2, where lambda is the wavelength of modulating wave, not the laser wave. So they are the same concept when phase based principles are there. So let us talk about the dependencies. That means if I consider the factors which affect the response or the return pulse, what are those factors? This is LiDAR equation. The reflectivity of the target is the most influencing factor. I will give you certain example of those. What does it mean? As we told, it is possible that within one footprint we are able to detect multiple returns. So let us see there is an area on the ground surface, and this is one footprint, that is 13.5% or 1 by e square size at a certain distance. Within this we have a wire line which is at some height from the ground, and because of this wire line, this is the, let us say, transmitted pulse, and I will get 2 responses. First is from the wire, which is more reflecting, I assume here, and this from the ground. This is ground response, and that is from the wire. What if I have 2 wires in one footprint? Let us say this and this. Okay, so this is ground. So this is ground here. Both wires are at the same height. We cannot distinguish between the heights of the two wires. So now they will get the one return from two wires and one return from the ground. Return will be higher. But remember, this is for the wires and this is for the ground. Because now two wires contributing towards the reflectance. Remember, this return pulse will be always less than the transmitted one. What is the third possibility? Assume that this is transmitter or receiver assembly, and along this line we have couple of objects. Let's say one is here, one is here, one is here. If this is the range R1, or if this is the height H1, this is the height H2, and this is the height H3, that means heights are increasing from this one, I will get responses like this, and like this from height H1, from H2, from H3. You can assume that all the factors are there, atmosphere, height and everything. Take one more case. There is a footprint here and there is some material here which is of uniform nature. Let us say sediment, and sediment has rho equal to 0.3, reflectance of 30%. So I will get a response like this, call it A. Now let us assume another case where in a footprint we have sediment like this. At the same time, we also have some kind of more reflecting areas like this, which is having very high reflectance. Let us say rho equal to 0.9. Okay, what will be the consequence? I will get response which is slightly higher, and I call it B. So the B is more than A for the same laser pulse. Let us take one more case and try to understand what is the effect of reflectivity. I have very small areas here which are having high reflectivity, but it is very small and they are also not concentrated one. They are away from each other as well as very small in the size. But here there is a big area of sediment. Here they are the reflecting particles, but they are very small in area. I will get this kind of response. Let us say C, and C is no doubt less than A, which is no doubt less than B. So this is the way we explain the effect of reflectivity on return pulse. What about the other factors? Range, which is affected by the average power as well as sequential firing. We have already discussed it before. Then we have the areas of transmitter, target and receiver. If I put all the factors in order, they are on the third order. That means they are on the third rank, they can affect the range measurement. The fourth one is the beam divergence, because it is creating the ambiguity in the footprint. And finally, these are the total factors which affect the range measurement by laser. Now, we have seen that laser is an active sensor. It can fire the pulses consecutively and it does not require any sunlight, so it can work in the night. And as a result, we can use the laser in a three fashion, using different platforms. In an aerial fashion, that means I am mounting laser scanner on an aircraft, and aircraft is carrying that and we are acquiring the data, or what we call airborne lidar data acquisition. Similarly, if I use some tripod or any terrestrial platform which is static, which is not moving, we call it the terrestrial platform. So I can use it like tripod and I can mount laser scanner and I can acquire the data. Similarly, what if I mount the laser scanner on a vehicle, and vehicle is moving on the roads and it is acquiring the data. So that is called the mobile laser scanning or mobile lidar scanning. So these are the three ways to acquire the lidar data. So I would like to make a summary of what we have learned today about laser as well as lidar. First, laser is a light. That means it behaves like a light. It gets diffract, it gets reflect, it gets refract, it gets polarized also. It also creates interference, destructive as well as constructive. But it is a monochromatic, having the same wavelength, and coherent, having the same phase. It is also scattered with the dust and water particles in the atmosphere. So now using laser we develop the lidar, that is light detection and ranging. Light detection and ranging is, or lidar is, an active sensing technology. So it does not require any external source of energy like sun. So I can use it in night also, like radar. Moreover, if you see carefully, it is least sensitive to the surface material. That means if I am having different land classes, for example ground, grass, tree, road or any other surface like buildings given in the same area, I can still use the lidar in order to detect all those. It is least affected by the multipath, weather and external factors. It is very useful for the large areas on ground, and you may find in the literature it is named by different names: lidar ranging, lidar mapping, lidar radar, altimetric lidar, lidar grammetry and lidar altimetry. Today we have learned the fundamentals of the lidar. In the next lecture, we are going to talk about how to use the lidar in order to acquire topographic data and what we call the topographic data acquisition. It is expensive also. We prefer to acquire for the large areas, or large areas can be easily covered by the airborne data acquisition. It does not mean that we do not use it for terrestrial platforms. We use it. However, with the airborne data acquisition, we can cover large areas. So we will look into these things in the next lecture. Here, I would like to say that whatever discussion I had today with you in this lecture, I have referred these books which are excellent resource. Thank you very much.